Amanti-Gi, you wanted to know what a bivalent pair is. A bivalent pair is a homologous chromosome. Now, I hate it when they say homologous pair of chromosomes, because homologous chromosomes already means that there is a pair. So look here. Have I got the right pen in my hand here? All right, so you've got, okay, as I did just now, these are called homologous chromosomes. Okay, now here you've got your your centromere. This is from your dad, so this will be paternal. This is maternal. So this is the maternal chromosome. And this is your paternal chromosome. Okay. Centromere. It merely holds them together. Now that and that, daughter chromatids. And the same here, daughter chromatids. All right. So when we have during metaphase, and I'm going to say metaphase 1 here, so you're going to have your chromosomes lined up there. So we're going to have I'm just going to do 2 pairs. Okay. And all right, here, when they sit like this, that's called a bivalent pair. Bi means 2. A bivalent pair means that those 2 there are your bivalent pair as well. They are your homologous chromosomes. So when you talk about homologous chromosomes, that means that they are a pair. Or you can call them bivalent. So I hope that clarifies that one. Some textbooks call them bivalent chromosomes or bivalent chromosome pairs. Homologous chromosomes is the easiest, bestest way, and all your best textbooks call them homologous chromosomes. Okay, then. Please explain random segregation. I'm not sure. Please explain random segregation before passing meiosis. Roland Dile, I don't know what you're asking me here. Okay, but just in case, I think it is what you mean about a random assortment. Now, let's just quickly do this. When we have random assortment, it's random, which means it doesn't matter what way. So if I've got my homologous chromosomes here, during metaphase 1, okay, they're the spindles, there's the centriole, they're all sitting here at the equator. Okay, there is my homologous pair of chromosomes. Okay, but the thing is, your spindles run all the way through. This chromosome could pull to that pole, and this one may pull to that pole. It doesn't mean that if they're on this side, they're going to automatically pull to this pole. It doesn't happen that way. It's random. Random. So if I've got number 1 and number 2 and number 3 and number 4 sitting like that, I can either have 1 and 3 pulling to this pole and 2 and 4 pulling to this pole. Okay? Or I can have I can have 1 and 4 pulling to this pole, and I can have 2 and 3 pulling to this pole. All right, so remember 1 and 2 are your homologous chromosomes, and 3 and 4 are homologous chromosomes. I could also say this is 1A and this is 1B, and this is 2A and this is 2B, and 1A, 1B, and 2A and 2B, if it helps you better. But it's random. They can go to any pole, but as long as one of the 2 homologous chromosomes, one of them is going to go one way and the other one's going to go that way. So they can either go this way, okay, or they can go that way. But it's random. And remember, we've got 23 pairs of chromosomes. So you've got an assortment. You may have 1A goes this way, 2B goes this way, 3A, 4A, 5A, 6B, they all channel to one side. The others will clearly go to the other side. So it's all random. Now, if you're talking about how random assortment actually plays a role in genetics, so if we go to genetics, which is paper 2, but let's tie it up. So for genetics, when we talk about random selection, it can also be called random assortment, and it could also be called random segregation. You see, so segregate means to separate. Assortment means to select. And selection, well, selection means assortment and segregation. So what we have here is Mendel. Mendel turned around and he said his law of random assortment and segregation is this. If I have on a chromosome, okay, a chromosome, and on that chromosome, so this will be the dad chromosome, and this is the mom chromosome, or the paternal and maternal chromosome. Okay? I'll have those are your alleles for, let's say, hair color. Or in the case of Mendel, let's be specific. Let's not do hair color. Let's do for height of sweet pea flowers. Because he did all his stuff with sweet pea flowers. Okay, what happened then, these are alleles. So those are all alleles. These are the alleles on the paternal chromosome, and this is on the maternal. Remember, ma, maternal, pa, paternal. Okay, so they're your alleles. They sit on the same locus. Okay, they're on the same locus. Now remember that these two are 2 daughter chromatids. And the same here, 2 daughter chromatids. So what's on this one is exactly the same on this one. And what's on this one is the same. It's duplicated on that one. All right. So they're on the same locus because we've got alleles. So there's the allele from the dad. And there's the allele for, no, we're not going to go dad. We're going to go, this will be pea plant 1, and this is pea plant 2. Okay, so we're talking about the height. So let's say this one here is for short. Okay, so what am I going to have? I'm going to have, or for tall, and this one will be for short. That means that after meiosis 1, okay, we are now going to have 2 haploid This is at telophase. I'm going to have 2 haploid daughter cells. Non-identical daughter cells. Oh, for heaven's sake. I'm trying to write too fast. Non-identical daughter cells. Okay? 2. So in this one, I will have for this pea plant, I'm going to have that one, the gene for tallness, and in this one, I'm going to have the gene for shortness. And they are going to separate out independently and randomly when the gametes are made. All right. And then when the gametes are made, they go into ovules, and you get a pollen that goes in there, and then it depends on what the pollen grain from the male part of the plant, the sweet pea plant, and the female. But those gametes, those characteristics, those alleles separate out separately. And that is what the whole random segregation is about. And that is in genetics. But it's based on meiosis. Okay, and then Mukulu says, yeah, I'm enjoying and I'm understanding. Mwah, happy. All right.